So far we were trying to visualize the predictions of a network. Now let's try to understand it. First of all, what does the title of the paper means? Understanding deep learning requires rethinking generalization. What is generalization? And in particular, what is generalization error? So you train your network on your training data set. You're going to make some error there, but you don't care about your training data. You want to use your algorithm in production and you want to test it first on your test data. And there is usually a discrepancy between the amount of error that you're making on your training data and the amount of error you're making on your testing data. And that difference is the generalization error. So that's the definition. So there is this question of why neural networks generalize. You have a lot of parameters in your network. You are training it on your data, on training data. Why isn't it overfitting? What's the reason that they generalize to your test data? So that's still an open question. And this paper tries to answer that a little bit, or it's at least moving in the direction of answering it, or maybe opening up room for some new questions. So you can start with the randomization test. And the observation is that deep neural networks can easily fit random labels. So they are powerful enough to overfit even to random labels. So let's take your ImageNet. Each image has a label. Now let's replace those labels with random stuff. Your labels are from 1 to 1000. Just replace it with random stuff and train your network on that random labels. This is your training data. And if you do that, there is no hope that your network is gonna generalize. Am I correct? For instance, if you have 10 labels and you randomize your labels and your network overfit on your training data, when you take it to testing, it's gonna be as bad as random predictions. Just pick something at random. When it comes to an image, pick a label at random, and that's gonna be reported as your prediction.
Is it not going to learn exactly the same thing, but we're just kind of changing what we're calling things? Like if you randomly change the label of dog to computer, it's still going to find all the dogs. It's just going to call them all computers. I suppose that my objection is that it's not completely random or stochastic. It's just being told the wrong names for things, but it's still discerning patterns, right?
I think Soroush has a good answer for all of us. So by random, it means it's going to be random, for example.
Okay. Yeah, definitely.
So we're saying we have a neural network that's 100% accurate where each of our training examples has its own random label.
Yes.
Okay.
So now let's see what happens. And we are going to make things more complicated as we go. One thing to notice is that you're going to do your training for a couple thousand steps, and all of these losses, the average losses, are going to zero. So you're overfitting on random labels. There is a question from Kevin. How can you be sure that random labels induce random patterns in images? For instance, maybe the subject is always near the middle of the frame.
I think the paper answered my question because they're also testing on random pixels, which seems to be pertinent than randomly labeled real images.
But what is the true test here? You're saying that our network, we are trying to understand generalization. So that's our objective. And there is a difference between training and testing. And the idea is that on random labels, your network is powerful enough to overfit even random labels. Now the question is, where is this generalization of the neural network coming from? If your network can overfit on random labels, it's going to be able to overfit on non-random labels. But then why is it generalizing when it comes to testing? So let's see.
But aren't we when we're training the network, aren't we actively attempting to prevent overfitting by using these regularization techniques and by not training for infinite time?
That's a great question. What we are going to do is break down and try to understand where this generalization is coming from. Is it coming from the network structure? That's the first question that we have. Is something special about deep neural networks that make them generalize? And then we are going to go into regularization. Maybe regularization has an effect. And then we are going to even turn that down as an explanation.
Okay.
So we are now making a hypothesis, and the first hypothesis that we are trying to reject is that, or maybe accept, is that there is something special about neural networks. So you can have your true labels, and yes, your network is going to train faster, and you're going to overfit. Not overfit, you're going to basically make your loss be zero after a couple thousand steps of training. The random labels are going to take longer to converge, but eventually they are going to converge to zero. So eventually you're going to be able to fit random labels. And then, as you said, you're going to make things more complicated as you go along. You can shuffle your pixels. Still, you're able to overfit. You can have random pixels, or you can random pixels with Gaussian distribution, just random noise. So random pixels, you still have the same pixels as your original image, but you are randomizing their location. And then you have Gaussian. So question, what data set were the networks in these graphs trained on? I think it's CIFAR10. And you have a couple of other observations. So the more corruptions you make, it's going to take longer to overfit for different networks, Inception, AlexNet, or multi-layer perceptron, a fully connected network. And the test error, we know that if you have more corruptions, there is not much correlation between your training data and testing data. And eventually, your network is going to do as bad as a random guess. So if you have 10 labels, and if you make a random guess, you're going to make an error with 10% probability. 90% error. And you're going to be correct only 10% of the time if you make your guess random. So eventually, you're going to approach random guessing. So what is the observation now? The observation is that the model architecture in itself isn't a sufficient regularizer. Why? Because given enough time, it's going to overfit. So does this make sense so far?
Yeah, this makes sense.
Now, the other observation is exactly what I think. And the question was, how about regularization? Usually we have early stopping in our networks, we have dropouts. These are explicit regularization. Yes, the observation is that they may improve generalization performance, but it is neither necessary nor sufficient for controlling generalization error. Yes, it helps, but it's not sufficient, and it's neither necessary. And what type of regularizations, explicit regularizations, do we use? We can have data augmentation, like random crops of your images. You can have weight decay. It is basically L2 normalization of your weights. And these are explicit regularizations. And on most of them, you're able to achieve training accuracy of around 100%. But when it comes to testing accuracy, and in particular, when it comes to fitting random labels, you're still doing as bad as random guessing. So that's this observation, that it may improve generalization, but it's neither necessary nor sufficient. So any questions so far? And here is another way of looking at the same observation. This one is now on ImageNet and CIFAR10. Now we are looking at accuracy, and we are making the argument that yes, regularization is gonna help with the performance. So this is without, this is with data augmentation, weight decay, and dropout. And this is for testing, and that's for training. So your training is always gonna be above your testing. Now we are considering the effect of without data augmentation. That's gonna be this red one. And the gap is expanding. So the gap between the blue curves was smaller. That's the generalization error compared to the gap between these red predictions. One of them is training, the other one is testing. And if you remove, if you include weight decay, it's not helping that much. Maybe because dropout is already helping us some. But that's the big picture, that generalization performance is gonna improve if you do explicit regularization. And we also have implicit regularization going on. That one seems to be more effective. And that's when you have early stopping. While training, you're going to look at your validation error. And as soon as your validation error starts going up, you're going to stop training. That's called implicit regularization. And that one seems to be helping more. But it's not enough. So any questions so far?
I guess this seems to me, like the plots just seem to be saying that, yeah, the generalization error is worse if you don't regularize, which is like the first sentence in that second box. But the second sentence says that regularization isn't necessary and isn't sufficient for controlling that error. So, but is that saying that, and I guess maybe that's where the implicit regularization comes in. But like we can develop a network where we never use any regularization techniques, but we can still get like theoretically a zero generalization error.
I don't think you can push the generalization error to be zero.
But really,
You're always gonna perform better on your training data compared to your testing, unless your model is underfitting, which is a bad thing. Also, you're not using the full capacity of your model.
I guess it just seems like this is trying to say something more than what it seems like it's saying. It just seems like it's saying that regularization helps.
No, it's exactly that sentence that I wrote here. It's regularization helps, but it's neither necessary nor sufficient. It's neither necessary, it's not necessary because this model is already doing good without any regularization. That's not a bad prediction. Regularization is helping a little bit. So that's why it's not necessary. And it's not sufficient because you can still make your network with all of its regularizations to overfit on the random labels and basically make the generalization error to be its worst case scenario. So I broke down these terms. Yes, it improves. These are signs of improvements. It's not necessary because this network is already doing good enough without augmentation or without dropouts. But and the other term that it's not sufficient because you can make your generalization error to be as bad as possible.
Okay, I see what you mean. Thank you.
But the main reason that I'm covering this paper is because of what I'm about to tell you now. And I hope we have enough time to cover it. So you know that neural networks are universal function approximators. I'm sure you have heard of it. That one is for approximating any function, and that one is for the infinite dimensional case. There is a nice theorem in this paper that I found really interesting. That's for finite dimensional case or finite number of data points. So it's a universal function approximators when you have finite samples. What does it mean? If somebody gives you finite samples, you can design a network that's going to overfit those samples. It's going to overfit your data points. And in that sense, it's universal approximator. But for that, we are going to need a lemma. Let's say you have two sequences, the sequence of B and the sequence of X, and they are interleaving. It means that B1 is less than X1, X1 is less than B2, B2 is less than X1, X2, and etc. until Bn is less than Xn. So they are interleaving. Out of that, you're going to get a matrix that is n by n, and you're getting it from subtracting xi minus bj. Those are going to be your entries of that matrix. And we are going to have a max of that entry and 0. So these are the entries of A. The observation is that this A has full rank, and we're going to see why. And its smallest eigenvalue is the minimum of xi minus bi. So please note the notation here. It's xi minus bj, and that's giving us aij. So that has to do with the eigenvalues probably being on the diagonal. So let's see.
It's going to be strictly lower triangular just by the construction of this interleaving sequence. Am I reading that correctly?
Perfect.
Okay.
So A is lower triangular because of this max operation and because of this assumption that x1 minus b1 is positive, x2 minus b1 is positive, etc. And the other way around is going to give you zeros. So yes, A is lower triangular. And if it is lower triangular, it's going to be full rank if and only if all the diagonal entries are non-zero. So now let's see whether this is true. Are all of the diagonal entries non-zero? For the diagonal entries, we are going to use this assumption that we made, xi is bigger than bi. So the maximum is positive on the diagonal, so they are non-zero, and A is invertible. And we know that a lower triangular matrix has its eigenvalues on the main diagonal, so we are all set. If all of the eigenvalues are on the diagonal, then its smallest is the minimum of the entries on the diagonal of that matrix. So is everything clear? Now, this is equivalent to universal function approximator, but you can say it's finite sample expressivity. How do you build your network? This is our network. You're going to have C of x. You're going to multiply x by a vector. That's the inner product. And x could be in RD, A is in RD, and the inner product is a number. It's a scalar. We are going to subtract bj. We are going to have n of them, as many of them as the number of samples. This is where the max is coming in. And we are going to have some weights. That's the construction of our network. And this network is going to overfit our data. Why is that? So this is our data, z1 up until zn. And we are going to try to find w, b, and a such that yi is c of zi. So how can we do that? Because if we manage to do that, our network is overfitting. You can choose A and B in this fashion. This is just a definition. You're going to say my xi is A times zi. So it's that term. And that's going to be a scalar. That's going to give you your xi's in the lemma. And then you can choose bi's. You have a lot of options with them. As long as they satisfy these inequalities, we are fine. So this one was just a definition. This is, as soon as you choose A, you're going to be able to choose B's. And you have infinitely many options for your B's, so it's doable. Now we are going to invoke that lemma, because now you have your xi's, you have your bi's, you have to solve a system. And that system, this matrix, maximum of xi minus bj is exactly that matrix that you have over there. And you're going to be able to solve it because it is invertible. So what did we just show? There exists a 2-layer neural network with ReLU activation. This is ReLU activation. That's going to be able to overfit any n data points. So somebody gives you n data points, and you're going to design your network such that you can overfit it. And then how do you make it deeper? You can trade your width with the depth, and that's going to give you a deep neural network. So a 2-layer deep neural network is able to overfit any finite sample of size n.
Is part of this proof the assumption that you can always find this vector A, so that given n samples z, you can find a, I guess, is that ranking necessarily dependent on A, or is it just you pick an A and then all of the inputs take an inner product with A, and then you can rearrange those numbers however you want? Like the inputs z1 through zn don't necessarily need to match up with the ordering x1 through xn.
So before I answer your question, I think we are over time. For those of you who want to leave, you can leave. And for those of you who have a question, you can stay and ask. And let's answer your question. I guess it has something to do with A. I mean, we are not that free with the choice of A.
Well, obviously, you pick A so that there's no ties. There's no equalities between the x's. But as long as they're all unequal, is that good enough? Because then we can just say, okay, we'll order them now according to whatever ranking came out.
Yes, so that can be fine.
Okay.
Because yes, you're right. The ordering here doesn't really matter, whether it's x1, x2, x3, or you can have different perturbations of them.
Yeah.
So yes,
as long as they're all distinct values.
Exactly. Then you can sort them, and then you can choose your BIs accordingly.
These are easy to choose then, and then you have a system that you know you can solve because of that theorem up above with the lemma.
Yes. And what you're solving for is you are solving for these W's.
Yeah.
And the message is that you can overfit any sample of finite size.
Got it. So it's just a proof theoretically that this is possible, not just that it's observed, but that it's guaranteed.
Yes. The figure on the left, we said that we had an observation that if your labels are random, you're going to be able to overfit. Now this is a proof that yes, it is actually possible.
The other question I had is about the significance in this table of the fitting with random labels. I guess I'm unclear on what they're exactly illuminating by this, like random label training, doing the generalization test, getting test accuracy of 10%, which is random guess. It seems to me like we've gone around full circle. Like we know that's going to happen if something's exactly perfected at classifying randomness. It's going to give us randomness.
But this is different. Now you have a neural network and you were making an assumption that there is something special about neural networks that they generalize.
Mm-hmm.
Now you have a counterexample to that. You say, I'm going to randomize my labels, and your network, if it manages to overfit, then there is no hope for generalization because of the problem setup.
Yeah.
And it actually happened. You train that network on random labels and it overfits. So I think the main problem is that the network is overfitting. And if it overfits, there is no hope for generalization. So
Yeah, I'll
let's
just
do
have to.
the counterexample route. So I'm going to claim that the model architecture is a sufficient regularizer. And that's my explanation for generalization error. So I'm going to claim that the model architecture is a sufficient regularizer, and that random test is going to be a counterexample to my claim, because that's exactly what they want to do. They say that the model architecture itself isn't a sufficient regularizer. And that's a counterexample to the argument that it is a sufficient regularizer.
Yeah. Well, that makes sense. Thank you.